Okay, let's take a look at practice exercise 2.11. Get back over there. Okay, F is equal to x prime y plus xz. And what's product of max terms? With the product max terms, remember this is what we're looking for. So multiply together and then addition between them. Or you can think of it as and or is between them. Well, I notice this first one is missing a z. So got that times, and from our postulates or theorems, x plus x prime is equal to 1. X or not x is equal to 1. So since we're missing a z, we'll have z or not z, because that's equal to 1. So I haven't changed it any. Now this next one's missing a y. So we'll do the same thing. Now I'm going to multiply this through. It's one of our properties, distributive property. Multiply this through. And I'm going to put in alphabetical order when I'm doing it. And x, y prime, z. Now, trying to remember where that property is located at. I'm searching. Okay, so this maybe demonstrates it. Where we take the complement of f prime, then we obtain this function. So we get this one right here. Specifically, as you look at it, to see how I rewrite it when everything's multiplication and there's an addition between them. And I'm not sure where the property is, but this shows you an example. See how this switches? X prime, Y prime, Z prime becomes X, Y, Z. So the multiplication, the and becomes addition or the or, and you have a complement of each one. This one is x, because x prime becomes x, y becomes y prime, z prime becomes z, and so forth. So, using that same principle here, x prime becomes x, and we're putting a plus between them, or an or, and y becomes y prime, z becomes z prime, x prime becomes x, plus y prime plus z. And this is x prime plus y prime plus z prime. And then this one's x prime, y, z prime. The thing of it is, I don't think that's what they got. Oops, why did I get that? Let's try that again. Plus y plus z prime. Assuming I wrote it down right. X prime y plus xz. X plus y plus z prime. No, they don't get that at all. Product of max terms. Let me check the book out. Assuming the property is right up above, I know we did it right. I think they got a typo there. Yeah, if it's following our example above, then I don't see how there's any way they can get what they got there. A lot of typos. Okay, draw a two-level logic diagram to implement the function b is equal to, so b c prime plus ab plus acd. And so, write that down. F is equal to b c prime plus ab plus acd. Another typo. Wrong in the book too. Sure enough, it's wrong in the book. Well, I'll talk about it anyway. See B C prime here? That matches the B C prime here. Okay. The AB that's there matches the AB that's here. Okay, we're so good. ACD does not match the ACD prime they put here, so they put an extra prime on this. And I guess I won't sketch over here. I was going to sketch it, but I'll just kind of go through this. A is coming down. It's going through an inverter, so this line here is A prime. B is coming down, is going through an inverter, that's B prime, C, C prime, D, D prime. Okay, so this first one is B and C prime. So we have a line coming over from B into our AND gate, and we have a line coming over from C prime into our AND gate. The next one is AB. So we have a line coming over from A, we have a line coming over from B into our AND gate. And then ACD, one coming over from A, one coming over from C, and this line here that's, oh, that is correct. So from D, this is just labeled wrong right here. that should be a D. And you can see that from here. It's coming from the D line, not from the D, the D prime. And then they're all going to OR gate, and that's what accounts for the pluses in between them. So that's how you draw a two-level logic diagram. Now, to do that, you have to either put in sum of min terms or product of max terms. Doesn't matter which one. So actually, your answer could be the other one too if you rewrote it the other way. And that's the end of that section. Other logic operations. They're talking about the truth tables for the 16 functions. So here's the truth table for the 16 functions, and the function they're talking about is down here. The null is where it's 0. That's our f sub 0. The and is like multiplication. That's operator symbol. The inhibition, can't say that word. X but not Y is written this way. Transfer is X. It's just a single X going through, so is Y. There's another word I can't pronounce. Looks like division. That's F2. So I come over here to F2, and division does not imply it here. You know, we are lucky with the multiplication. It was a straight multiplication, but this what looks like division is not that, but X but not Y. So if we come up here, 0, 0, 1, 0. I'm trying to see the pattern on this. X but not Y. It looks like that's when X is 1 and Y is 0. That's when it gives you a 1. Otherwise, it gives you zeros. How about this other one? Y but not X. That would imply that it's where Y is 1 and 0 is X. Let's see. F4. Y is 1, 0 is X. Okay, so that's true. Exclusive OR. X or Y but not both. So that would imply either X is 1 or Y is 1, but they both can't be 1. That's F6. And that's true. So where they're both 1 or both zeros, it's 0, otherwise it's 1. Now these I don't remember. I remember the main ones, but I have to refer back to this table when I'm doing this. The X or Y, we've seen that so many times, it's not even funny now. The NOR, and this is a symbol goes to the NOR. That's not OR. And you see that they have here X plus Y inside of parentheses and then the prime on there. So that takes the complement of X or Y. So if you look up here at the OR, which is 7, 0, 1, 1, 1. The NOR, which is F8, is 1, 0, 0, 0. The equivalence, you see the notation here. We take our exclusive OR up here, and we take the prime of it. So this is where X equals Y. So that's where both are 0 or both are 1. Then it gives you 1. Otherwise, it gives you 0. Complement is opposite. Implication. If Y then X. 11. If X then Y. Not sure if I see a pattern on that one. But anyway, you see the truth table up there. Complement, more implication. We'll look at NAND gate. And you can see the notation here. It takes your and takes the inverse of it, the complement. So the NAND. NOR is same as that. So NAND and NOR should be fairly simple to come up with. Identity is 1. It's always 1. Look at 15. You see it's all ones. I'll talk a little bit more about what we just did. Okay, digital logic gates. Since Boolean functions are expressed in terms of and, or not operations, it's easier to implement a Boolean function with these type of gates. Still a possibility of constructing gates for other logic operations is of practical interest. Factors to be considered to be weighed in considering the construction of other types of logic gates are the feasibility and economy of producing the gate with physical components, the possibility of extending the gate to more than 2 inputs, and the basic properties of the binary operators such as commutative and associative, and the ability of the gate to implement Boolean functions alone or in conjunction with other gates. Of those 16 we just talked about, 2 are equal to constant and all 4 are repeated. There are only 10 functions left to be considered as candidates for logic gates. And they list them there. Down here they show this. So we got our AND gate. We're seeing that. We got our OR gate, excuse me. And we're seeing that. Our inverter, we've seen that. Now the buffer is like something that slows it down. You've heard the term it's buffering. Well, it's maybe streaming a video, and it's taking time for it to get enough into the buffer such that it can play it without being horrible viewing wise. So it makes you pause. That's what a buffer does. And you see X coming in as 0, it goes out as 0. X coming in as 1, goes out as 1. So it doesn't change, it slows it down. The NAND gate is our and then we have a little circle in the front, indicating you do the and then you just invert it. Like here, 0 times 0 is 0, and then invert it, becomes a 1. 0 times 1 is 0, invert it, well, 0 times 1 is 0, invert it, becomes a 1. 1 times 0 is 0, invert it, becomes a 1. 1 times 1 is 1, invert it, and gives you 0. So that's an AND gate. Now a NOR gate. Again, we have the OR right here, and then we put a circle in the front. That circle inverts or takes complement of the result. So remember the OR we add like normal. So 0 plus 0 is 0. Complement, invert it, becomes a 1. 0 plus 1 is 1, invert it, becomes a 0. 1 plus 0 is 1, invert it, becomes a 0. 1 plus 1 is 1, invert it, becomes a 0. Now, exclusive XOR. That's where either X is 1 or Y is 1, but not both. So, and you can see that here. That's 0. Here Y is 1, so and X is 0, so that's a 1. Here X is 1 and Y is 0, and that's a 1. Again, the condition is only one of them can be a 1. On this one where they're both 1s, see how it gives a 0. So that's what comes through the gate when you do that. Now you look at this, that looks like the same symbol as our exclusive OR up here. Exclusive NOR means you put a circle in the front and that flips it to the opposite. The complement inverts it. So here, 0 and 0 would give us 0, inverted becomes a 1. Here, for our exclusive OR, 0 XOR 1 would give us 1, inverted becomes a 0. 1 XOR 0 gives us a 1, inverted becomes a 0. 1 XOR 1 gives us 0, inverted becomes a 1. So that's exclusive NOR. I got a drink here. And that's just talking about what we just talked about. Now, if you got more than 2 inputs, gates shown in figure 2.5, except for the inverter and buffer, can be extended to have more than 2 inputs. The inverter and buffer only have 1 input coming in. So you can't extend it to more than 2. Gate can be extended to have multiple inputs. The binary operation represents as commutative and associative. The and or operation is defined in Boolean algebra possesses these 2 properties. For the or function, we have this, and for associative, we have this. So commutative, where you can flip them around. Associative, where you can move. Here we got we're doing the x or y first. You can put it around the y and z and do the y or z first, or you can simply get rid of those and handle it from left to right. So it tells you or function can be extended to 3 or more variables because it handles the commutative and associative. NAND and OR are commutative, and gates can be extended to have more than 2 inputs. Now, how it would look like, with 2 of these gates here is you have X coming in, Y coming in, and then its output is coming down here. And remember, this is a symbol for the OR, so this is the NOR. So X NOR Y, and then that result comes into here, and you NOR that with Y. And there's your notation. Now, look at this right here. Okay, so on the other hand, if I have the X coming like this, and then the Y and Z coming in like this is Y NOR Z, and its result coming in here, and X is coming into that, and we're doing NOR, and it gives you this. Well, what's the difference? Well, here we group the X and Y together, and you see the parentheses here. Down here, we group the Y and Z together. See, we put parentheses around the Y and Z here as we write it. What this is showing, difficulty is that NAND and NOR gates are not associative. So this down here, we got our X or Y inside of parentheses, and then down here we got the Y or Z. So it changes the operation. Down here, there's between the Y and Z, there's a plus, and here right before the Z is little typo there. Let me see if that's wrong in the book too. Look, 3rd typo we found today. It's right in my paper copy of my book, but it's wrong here. No, it's wrong in the book, the paper copy. If you look at the inputs over here, you got X, Y, and Y. There is no Z input. This last one should be a Z. But anyway, what they're trying to demonstrate here is they don't give you the same. Then they're demonstrating that. I'm not going to go over that. But in reality, we don't split them up into like 2 separate NOR gates or 2 separate NAND gates. You can have multiple inputs coming in, like that. Now, I don't know what the maximum is you can have coming into a NOR gate or to a NAND gate and so forth. But it shows you here, you can have these A, B, C coming into a NAND gate, D and E coming into a NAND gate, and then their results coming into a NAND gate. So if you got too many inputs, doesn't mean you can't design your circuit. You just have to add more NAND gates to cascade them like this. And here's the result of that. You see we got A and B and C. That's the ABC you see here. And then a little circle on here does the prime there, the invert. D and E There's D and E, and then we have a little circle in the front, and that does that prime there, inverts it. And then we have an invert on the outside. That's because we're multiplying these two together. So that's this, or anding them together. And then we're inverting it, which makes it an and. So that's that. And then you see that gives you this right here. Second expression obtained from one of De Morgan's theorems. Also shows an expression in a sum of products form can be implemented with NAND gates. Because this right here is in the sum of products. NAND gate and NOR gates are explained further in section 3.6. The exclusive OR and equivalence gates are both commutative and associative and can be extended to more than two inputs. However, multiple input exclusive OR gates are uncommon from the hardware standpoint. In fact, even a two-input function is usually constructed with other types of gates. Moreover, the definition of the function must be modified when extended to more than two variables. Exclusive OR is an odd function. Is equal to 1 if the input variables have an odd number of ones. I think about that one. Exclusive OR, because if I did 0 and 0 first, that'd be 0, another 0, 0. 0 and 0 first here, 0, 0 XOR 1 will give you 1, because exactly one of them has to be a 1. 0 XOR 1 is a 1, 1 XOR 0 is a 1, okay. 0 XOR 1 is 1, 1 XOR 1 is 0, okay. So 1 XOR 0 is 1, and then 1 XOR 0 is 1. And 1 and 0, or 1 XOR 0 is 1, 1 XOR 1 is 0. And then 1 XOR 1 is 0, 0 XOR 0 is 0. And then 1 XOR 1 is 0, 0 XOR 1 is 1. Okay, so the number of ones is odd, gives you 1. If the number of ones is even, gives you 0. Okay, I see it now. The construction of a 3-input exclusive OR gate is shown in figure 2.8. So you see that down here. Function normally implemented by cascading 2-input gates as shown in A. Graphically can be represented as a single 3-input gate shown in B. Truth table in C clearly indicates the output F is equal to 1 if only one input is equal to 1, or if all 3 inputs are equal to 1. And they say we'll talk about it further later. Okay. Positive and negative logic. Binary signal at the inputs and outputs of any gate has 1 or 2 values, except during transition. One signal value represents logic 1 and the other logic 0. Since 2 signal values are assigned to 2 logic values, there exist 2 different assignments of signal level to logic value, as shown in figure 2.9. The higher signal level is designated by H, and the lower is designated by L. Choosing the higher level H to represent logic 1 defines a positive logic system. So up here, we got 1, and we got that specified as H. That's our positive logic. And when we say signal level, again, we for the most part, we think of like voltage going through. Choosing the low level L to represent 1 defines a negative logic system. And down here, the L, you see they attach to the 1. The terms positive and negative are somewhat misleading since both signals may be positive, both may be negative. It is not the actual values of the signal that determine type of logic, but rather the assignment of logic values to the relative amplitudes of the 2 signal levels. If you haven't had trig yet, in trig, if I looked at a trig function, this number that's in front here, and this just gives you the idea of what we're talking about with the amplitude. This number here in front is, you call it your amplitude. And if there's no number there, it's by default 1. And what that means is your graph bounces back and forth between 1 and -1. That's your amplitude. Amplitude is actually the absolute value of A. So here our amplitude is 1. Because if this was a -1, it'd still be 1. When you're talking about any kind of signal going, then it has this pattern of this sort. So that's what we're talking about, the amplitudes. Hardware digital gates are defined in terms of signal values such as H and L. It's up to the user to decide on positive or negative logic polarity. For example, consider, for example, electronic gate shown in figure 2.10 B. Okay, that'd be this one right here, this gate block diagram. Truth table for this gate is listed in A, this over here. Again, this is a generic gate that they're indicating here. And then you got your truth table. Remember, the H could represent 1, the L could represent a 1. Specifies physical behavior of the gate when H is 3 volts and L is 0 volts. The truth table down here. Okay, let me think about this. H is 1, so we're saying H is equal to 1. So put zeros in for the L. 0, 0 gives you 0. And this is an AND gate at this point. 0 for L, 1 for H. That's 0 and 1 here, which gives you 0. 1 for H, 0 gives you 0. And then both these are H's, so they're both 1s, it gives you 1. Now, on the other hand, if you go with the negative logic, then see how this becomes 1, 1? That's because the L's are 1s. So that's 1, 1. So you got 1, 1 there, and then you go down through there. Notice how the negative logic is specified with that symbol. So if you see that symbol, that's referring to your negative logic. That's still an OR gate. It's just a negative logic. Now considering, okay, talk about that. Small triangles in the inputs and output designate a polarity indicator, presence of which along a terminal signals that negative logic is assumed for the signal. Change from positive to negative logic to change into 1s to 0s, 0s, 1s. Okay. Okay, let's see how this goes. Got A's, B's, C's, D's coming in. This is drawn a logic diagram. And you have your inverters for this A prime, this is B prime, this is C prime, this is D prime. Now, they're all coming into, three of them. They're coming into an OR gate because there's pluses between them. So we have D coming in. So that's coming over from D into the OR gate. Then we have B and C, BC. B is coming from there. C is coming from there. It's coming into an AND gate, and that's coming into your OR. Now here we got two things, two additions or ORs that are coming into an AND gate, the multiplication. So our first one is D plus C prime. So D is right here. C prime is coming in from there. Okay, that's correct. The next one is A prime plus C. A prime is over here. So that's coming in. C is coming in from here. And both those coming in the AND gate. That's what creates this right here, which then comes into our OR gate. So that's how you do your logic diagram for that. Implement the Boolean function f is equal to xz plus x prime z prime plus x prime y with NAND gate and inverter gates and NOR and inverter gates. '73. Be on the previous page. But anyway, how you represent them is listed up above. Like to achieve this effect, then you'd have your ABC and then a prime or the inverter times or and D and E and then our inverter and then an inverter on the outside. Okay, so what they did down here, I need to find out where those formulas are so I can put them here. Oh. No, that's not it. But anyway, this is what we've seen in a few examples. I showed this earlier in this class, but they're separated by pluses. And we got a property that says you can rewrite those with multiplication between them or ands, which they did. And by doing that, you have to invert each one of these when you rewrite them with multiplication. So you see it becomes xz prime, and this becomes x prime z prime prime, and then x prime y prime. Now that gives us our complement. Then that down here, to undo the complement, you have to take the complement of it. So they just put a bracket around all of that and take complement of that. And then that's in the form that we saw up above, of our NAND gate. Now over here, we're still starting with F. And we got a property that says you can rewrite those as, we've got our pluses here. We can rewrite as multiplication between them. And the xz becomes x prime plus z prime. So the multiplication or and becomes addition or. X prime z prime becomes x plus z, and x prime y becomes x plus y prime. And that's specifically for the complement. Again, I don't know where those properties are, but we saw those earlier. Then you have to invert that to get to this. So this is kind of going the other direction. Our multiplication becomes addition, like that. And we invert each one of these. And I didn't see this up above, but this must have been the form of the NOR gates. Okay, integrated circuits. An integrated circuit IC is fabricated on a die of a silicon semiconductor crystal called a chip. Can contain electronic components for constructing digital gates. The complex chemical and physical processes used to form a semiconductor circuit are not a subject of this matter. Various gates are interconnected inside chip to form the required circuit. The chip is mounted in a ceramic or plastic container, and connections are welded to external pins to form the integrated circuit. The number of pins may range from 14 on a small IC package to several thousands on a larger package. Each IC has a numeric designation printed on the surface of the package for identification. Vendors provide data books, catalogs, internal websites contain descriptions and information about the ICs they manufacture. Got different types of categories. They're categorized according to the complexity of the circuit. You got small scale integration, SSI. Devices contain several independent gates in a single package. Inputs and outputs of these gates are connected directly to pins in the package. Excuse me. The number of gates is usually less than 10, is limited by the number of pins available in an IC. You got medium scale integration, MSI. Have a complexity of approximately 10 to 10,000 gates in a single package. These usually perform elementary digital operations. MSI digital functions are introduced in Chapter 4 as decoders, adders, and multiplexers, and then Chapter 6 as registers and counters. Now, your large-scale integration, LSI, contain thousands of gates in a single package. They include digital systems such as processors, memory chips, and programmable logic devices. They are presented in Chapter 7, which we don't get into. So these are the CPU processor. Might be one of those. VLSI, very large scale integration, or ULSI, ultra large scale integration, contain millions of gates within a single package. Examples are large memory arrays and complex microcomputer chips. VLSI devices have revolutionized the computer system design technology, giving the designer the capability to create structures that are previously uneconomical to build. So some of the innovations we're seeing in the performance of some of the new machines, they got an i9 out now. Some of the supercomputers you may see that they have available, that's all becoming possible because of this. You got digital logic families. And we'll go into this a whole lot, but TTL, transistor logic, ECL, emitter coupled logic, MOS, metal oxide semiconductor, and CMOS, complementary metal oxide semiconductor. These are classified under complexity, but also by the specific circuit technology to which they belong. Circuit technology is referred to as digital logic family. CMOS you maybe heard about before. That's in the computer. These other ones, TTL, boy, that rings a bell, but I don't remember if that from the computers or from this class. TTL is a logic family, has been used for 50 years, considered to be a standard. ECL has an advantage in a system requiring high-speed operation. MOS suitable for circuits that need high component density, and CMOS is preferable in systems requiring low power consumption. Some more definitions. Fan-out specifies the number of standard loads that the output of a typical gate can drive without impairing its normal operation. Fan-in is the number of inputs available in a gate. Power dissipation is the power consumed by the gate, must be available from the power supply. Propagation delay, average transition delay time for signal propagate from input to output. And noise margin is the maximum external noise voltage added to an input signal does not cause an undesirable change in the circuit output. They talk about using some of these tools to design these circuits. Obviously, since some of these contain millions of transistors and gates, it would not be possible to do them one at a time. How long would it take you to design a million transistors? So we got programs that help us do this. And this just talks about some of the tools and so forth. Specifically, this is where it has become beneficial. Important development and design digital systems, use of a hardware description language, HDL. Now, this will not be a language like you're used to. So it's going to be a little strange. You just don't have your standard for loop and while loop and so forth. It's not really of that type. It resembles a computer programming language, but is specifically oriented to describing digital hardware. So it represents logic diagrams and other digital information in textual form. The HDL description of a circuit's function can be abstract without a reference to specific hardware, thereby freeing the designer to devote attention to higher level functional details. Besides HDL type languages, we have ones that narrow down further, Verilog and VHDL. These are used by design teams throughout the world and are standards of the IEEE. And we'll be programming in Verilog and VHDL. Seems like there's another one we program in too. And that's the end of that chapter. Now, we won't go into the next chapter today, but next chapter is chapter 3, gate level minimization. So I'll go ahead and stop the video there.